All right, let's dive in. Today, we're tackling something I know you're all eager to understand better: chemical reactions.
Yeah, those fascinating transformations of matter.
Exactly. And we've got some great sources to guide us: Wikipedia articles on chemical equations and electrochemistry, even a bit on the history of the field.
It's like a roadmap through the molecular world.
Love that analogy. So, to start, we got to learn the language of this world, right? Chemical equations. Gotta admit, that phrase always makes me think back to high school algebra. Not my favorite memories.
I hear you. But think of chemical equations less like scary math problems and more like, well, elegant recipes.
Okay, I like where this is going.
They tell us what we're starting with, the ingredients or reactants, and what we end up with, the final dish or product. And like any good recipe, they follow a specific format.
Right, so reactants on one side, products on the other, an arrow pointing the way, and usually some numbers sprinkled in there.
Those are the stoichiometric coefficients.
Ah, yes, those. What exactly is the deal with those?
They tell us the exact proportions of each reactant and product involved. Like in a recipe, you need a specific amount of each ingredient. Otherwise, the dish is ruined.
So it's all about precise proportions, not just throwing things together randomly.
Exactly. And there's a beautiful balance to it all. Notice how the same types and numbers of atoms show up on both sides of the equation. It's a reflection of a fundamental law, the conservation of mass. Atoms can be rearranged in a reaction, but never created or destroyed.
So it's like a perfectly choreographed dance. Atoms just shuffling partners, nothing disappears, nothing appears out of thin air.
That's a great way to put it. And to ensure the dance is perfectly synchronized, we need to make sure our equations are balanced. That's where those coefficients come in.
Now you've got me thinking about balancing equations like a puzzle. Can you walk me through it?
Absolutely. Let's take methane combustion. What happens when you burn natural gas? The unbalanced equation looks like this. CH4 plus O2 yields CO2 plus H2O. We need to adjust those coefficients until we have the same number of each type of atom on both sides.
So same number of carbons, hydrogens, and oxygens. Let's see, we start with 1 carbon and 4 hydrogens on the left. We have that on the right too, but the oxygens are off, 2 on the left and 3 on the right.
You got it. To balance the oxygens, we can put a 2 in front of the O2 on the left. Now we have 4 oxygen atoms on each side. But wait, now we've messed up the hydrogens.
Right. To fix that, we can put a 2 in front of the H2O on the right. That gives us 4 hydrogens on both sides. So the balanced equation is CH4 plus 2O2 is CO2 plus 2H2O. Did I get it?
Nailed it. Now the equation accurately reflects the fact that no atoms are created or destroyed during the reaction.
Pretty amazing. I'm guessing this balancing act is crucial in real-world scenarios, not just theoretical chemistry problems.
Absolutely. Think about designing a car engine. You need to know exactly how much fuel and oxygen to mix for complete combustion. If the equation isn't balanced, the engine won't run efficiently. You might even create harmful byproducts.
So those coefficients are the key to clean and efficient combustion. Now that we've tackled the language of equations, I'm ready to dive into a specific type of reaction: electrochemistry. What makes these reactions special?
Well, electrochemistry focuses on reactions where electrons, those tiny negatively charged particles, are transferred between substances. They're like the energy currency of the molecular world.
Yeah.
And these reactions are not just fascinating, they underpin many technologies we use every day.
Okay, I'm intrigued. But before we jump ahead, can you break down exactly what happens during these electron transfers?
Of course, we're basically talking about 2 processes. Oxidation, where a substance loses electrons, and reduction, where a substance gains electrons. The key is they always happen together.
Like a give and take, a delicate dance. One loses, one gains.
Precisely. And this dance is what generates electrical current. Imagine burning wood. That's rapid oxidation, releasing energy as heat and light.
Right, combining with oxygen in the air.
Exactly. Now, in a battery, we're controlling that oxidation, harnessing those electrons to create a flow of current, taming fire in a way to power our devices.
Whoa, so we're controlling energy flow at the molecular level? That's incredible. But how do we manage this controlled oxidation? Where do these electron transfers actually happen?
They occur at special surfaces called electrodes. The electrode where oxidation happens is called the anode. The electrode where reduction happens, the cathode.
Okay, so anode, electrons lost; cathode, electrons gained. This is starting to connect to things like batteries.
You're right on track. Electrochemical reactions are the heart of batteries. but they're also essential for a surprising range of other technologies. We'll get into those a bit later.
Well, now I'm even more curious about all the applications. But before we dive into the modern world, I think it would be fascinating to understand how we even discovered this electron dance. Where does the story of electrochemistry begin?
Well, the roots of electrochemistry trace back to some rather shocking observations about frog legs.
Frog legs. Okay, now this is getting interesting.
It might sound strange, but back in the late 1700s, a scientist named Luigi Galvani noticed something really peculiar. While he was dissecting frogs, he observed that the legs of a dead frog would twitch when touched with metal instruments.
Okay, that's something I definitely would not want to see during a dissection. So what did he think was causing these twitching frog legs?
Galvani believed that he had discovered a new kind of electricity. He called it animal electricity because he thought it was coming from within the frog's tissues.
So he thought the frog legs were generating their own electricity. That must have caused quite a stir in the scientific community.
It definitely did. And then another scientist, Alessandro Volta, came along and challenged Galvani's theory.
Uh-huh.
Volta believed that the electricity wasn't coming from the frog itself. He thought it was actually coming from the contact between two dissimilar metals. You see, Galvani was using metal instruments, right?
So the metal was the key, but how did Volta prove his point? Did he stop dissecting frogs?
Well, dissecting frogs wasn't really Volta's thing. He was much more interested in understanding the nature of electricity itself. So instead of dissecting frogs, he went on to build something truly revolutionary, the first electric battery.
Wow. So how did he do that?
He stacked alternating discs of zinc and copper, separated by cloth soaked in salt water, and this created a circuit that generated a continuous flow of electricity.
So no more twitching frog legs, just a steady stream of electrons. It sounds like Volta's invention really changed everything.
Absolutely. The voltaic pile, as it was called, proved that electricity could be generated chemically, and it paved the way for a whole new era of scientific exploration and technological innovation.
And I bet it probably sparked quite a debate between Galvani and Volta.
It definitely did. And that debate actually helped advance the understanding of both electricity and biology. So it was a win-win for science in the end.
What a productive rivalry. So Volta's battery showed us that chemical reactions can create electricity, but can we also go the other way? Can we use electricity to drive chemical reaction?
That's a great question, and the answer is absolutely yes. In fact, just a few years after Volta's invention, two other scientists, William Nicholson and Johann Wilhelm Ritter, discovered that they could use electricity to decompose water into hydrogen and oxygen gas. This process is called electrolysis.
So it's like running a fuel cell in reverse, right? Instead of producing electricity from hydrogen and oxygen, they were using electricity to break water apart.
Exactly. And that discovery opened up a whole new world of possibilities. Suddenly, we could use electricity to break down compounds, extract elements, and even synthesize new materials. It was a real breakthrough.
So electrolysis was more than just a scientific curiosity. It was a powerful new tool that scientists could use.
Exactly. And then along came Michael Faraday, who really amplified the significance of electrolysis. In the 1830s, he did all these really meticulous experiments that led him to formulate his two laws of electrolysis. And these laws precisely link the amount of substance transformed in an electrochemical reaction to the amount of electrical charge passed through the system.
So Faraday essentially gave us the quantitative framework for understanding and predicting the outcomes of electrolysis. That must have been a game changer for fields like chemistry and engineering.
Absolutely. Faraday's laws laid the foundation for countless technological advancements. Everything from electroplating, which is used to coat objects with a thin layer of metal,
Right.
to the industrial production of important chemicals like chlorine and aluminum.
This is just incredible. In just a few decades, we went from twitching frog legs to the industrial scale production of chemicals. The field of electrochemistry advanced at an unbelievable pace.
It really is a testament to human ingenuity and the power of scientific inquiry. And thankfully, that spirit of innovation continues to drive the field forward today.
So we've explored this amazing history of electrochemistry, from those early observations with frog legs to the development of tools like electrolysis. But honestly, I'm really curious to dive deeper into how this science is used today. How do we see electrochemistry in action in our everyday lives?
Well, I'm willing to bet you have at least one device in your pocket right now that relies on electrochemistry. A battery.
Ah, of course. Batteries power our smartphones, our laptops, even electric cars. They're everywhere.
Huh.
But how do those batteries actually work? I know it has to do with chemical reactions and electron transfers, but can you break it down for me?
Sure. Batteries are basically self-contained electrochemical cells that convert chemical energy into electrical energy. And they consist of two electrodes, we've already talked about those,
Hmm.
an anode and a cathode. And these electrodes are immersed in an electrolyte.
Okay.
The specific chemical reactions going on inside a battery depend on the type of battery, but the basic principle is always the same.
Yeah.
There's a controlled flow of electrons driven by a difference in electrochemical potential.
So it's basically like a miniature version of Volta's pile, but this time those controlled electron transfers are happening inside the battery.
You got it. And there's so many different types of batteries out there. Would you like to focus on one specific type, like the lithium-ion batteries that we find in our smartphones and laptops?
Yeah, let's talk about lithium-ion batteries. They're really everywhere these days. So how do those lithium ions move around inside the battery to generate electricity?
Imagine it this way. During discharge, lithium ions flow from the anode, which is usually made of graphite, through the electrolyte, to the cathode, which is usually made of a lithium metal oxide. And as these lithium ions move, they release electrons, which creates an electrical current that powers your device.
So the lithium ions are like tiny couriers delivering electrons from the anode to the cathode.
That's a great way to think about it. And when you plug in your phone to charge it up, this whole process is reversed. An external voltage pushes the lithium ions back to the anode, storing the energy for later use. And this is what makes lithium-ion batteries rechargeable.
So it's like a game of electrochemical ping pong, with the lithium ions bouncing back and forth between the electrodes and carrying those electrons with them.
That's a great analogy. But like a ping pong ball that loses a bit of its bounce with every hit, a battery's ability to store and release energy diminishes over time. And that's because of things like the formation of unwanted side products on the electrodes.
Ah, so that's why our phone batteries eventually give out and we need to get new ones. They just can't keep up with the game anymore.
Well put. But even though batteries have their limitations, researchers are working really hard to improve their performance. They're trying to increase the energy density, the lifespan, and the safety of batteries.
So we've got these tiny powerhouses, these batteries that are packing a lot of electrochemical energy into a small package. But I'm wondering, what about the larger scale applications of electrochemistry? We talked earlier about fuel cells, and it seems like they offer a lot of promise for a cleaner energy future.
Fuel cells are another great example of how we can use electrochemistry to generate electricity. And unlike batteries, which have a fixed amount of energy that they can store, fuel cells continuously convert the chemical energy of a fuel, usually hydrogen, into electrical energy.
So they're more like tiny power plants that keep generating electricity as long as they have fuel, right?
Exactly. They don't need recharging, just a steady supply of fuel.
That seems ideal for powering cars and homes. No more range anxiety or waiting hours for your car to recharge.
Absolutely. And unlike combustion engines, which produce a lot of harmful emissions, fuel cells primarily emit water vapor, making them a very clean energy technology.
I'm sold on the idea, but can you paint me a picture? How does a fuel cell actually work?
In a typical hydrogen fuel cell, hydrogen gas is fed to the anode where it is oxidized, and this releases electrons.
Okay.
At the same time, oxygen from the air is fed to the cathode, where it is reduced by accepting those electrons.
So it's like the hydrogen is giving up its electrons at the anode, and the oxygen is over at the cathode just waiting to grab them up.
Exactly. And that flow of electrons from the anode to the cathode generates an electrical current, which can be used to power anything from a car to a house.
And the only byproduct is water. That's amazing. But I imagine there must be some downsides. What are the challenges we need to overcome before fuel cells become as widespread as batteries?
You're right, there are challenges.
Yeah.
One of the big ones is storing and transporting hydrogen safely and efficiently.
Yeah.
You see, hydrogen is flammable and needs to be stored under high pressure or at really low temperatures, and that can be tricky.
So we still need to work on the infrastructure for a hydrogen economy.
We do. But even with those challenges, fuel cells have a lot of potential. They're already being used in certain applications like forklifts and buses, and as the technology develops, we can expect to see them playing an even bigger role in our energy future.
So we've got these batteries and fuel cells, both powered by electrochemistry. It seems like this field is already having a big impact on our world.
It definitely is.
Oh.
And that's just the beginning. Electrochemistry is also playing a crucial role in all sorts of other technologies and processes. Remember electrolysis?
Mm-hmm.
Well, it's not just for splitting water. It's also used in industrial processes to produce chlorine, sodium hydroxide, and even aluminum.
Wow. So a lot of the everyday products that we take for granted rely on electrochemistry.
They absolutely do. And let's not forget about electroplating. That shiny chrome finish on your car, electroplating, the gold on your jewelry, also electroplating.
It's really amazing how electrochemistry can be used to coat objects with thin layers of metal for things like protection, decoration, or to improve their conductivity.
And then there are electrochemical sensors, which are used in everything from medical diagnostics to environmental monitoring.
Oh, wow.
These sensors rely on the subtle changes in electrical signals that occur during electrochemical reactions to detect specific substances.
Okay, so electrochemistry is a lot more diverse than I thought. Batteries for our devices, fuel cells for a cleaner future, and all these industrial processes relying on the precise control of those redox reactions.
It really is a versatile field. And as researchers continue to push the boundaries of electrochemistry, we can expect to see even more innovative applications in the years to come.
Okay, so before we get lost in all the future possibilities, I think it's time to start wrapping up this part of our deep dive.
Yeah, I think that's a good idea. We've covered a lot of ground today, everything from the basic principles of electrochemistry to its really wide-ranging applications.
That's right. Be sure to join us again for the final part of our deep dive, where we'll be exploring all the exciting possibilities that electrochemistry holds for the future. And we're back for the final part of our deep dive into electrochemistry. After all that, I'm supercharged to talk about the future of this incredible field.
It's a future brimming with possibilities. Electrochemistry holds the key to solving some really big challenges we face.
You know, when we talk about things like batteries and fuel cells, it feels like we're already living in the future. But what's next? What kind of breakthroughs are on the horizon?
Imagine electric cars with a range of hundreds of miles, recharging in minutes. That's the promise of next-gen batteries.
Charging my car as fast as filling up a gas tank, that would be amazing. But I know there are hurdles to overcome with batteries. What are researchers focusing on to make these super batteries a reality?
One really exciting area is solid-state batteries. Traditional lithium-ion batteries use liquid electrolytes, which, can be flammable and they limit how much energy you can store. But solid-state batteries use a solid material, which is safer and could really boost energy density.
So, trading in a leaky, flammable container for a super efficient, solid one sounds like a game changer. But what about renewable energy, like solar and wind? Storing that is a huge challenge, right?
Absolutely. And electrochemistry offers some elegant solutions. Flow batteries, for instance. They're perfect for storing energy on a large scale, like for the whole power grid. Think of them as giant rechargeable battery tanks. Need more capacity? Just use bigger tanks.
So we're just pumping liquids around to store energy. That doesn't sound very efficient.
I know it might sound a bit strange, but flow batteries have real advantages. They can be charged and discharged many times without degrading, which is perfect for intermittent renewables like solar and wind. Plus, they have a long lifespan and are fairly safe.
So it's like having these huge energy reservoirs. Soak up excess solar power during the day, then release it at night when the sun's gone down. That's vital for moving towards a future powered by renewables.
Exactly. And let's not forget sustainable manufacturing. A lot of traditional chemical processes use harsh chemicals and produce a ton of waste. Electrochemistry offers a cleaner, more efficient way to do things.
So instead of harsh chemicals, we're using electricity to drive reactions, but in a much more eco-friendly way.
Precisely. Electrosynthesis, for instance, can create things like pharmaceuticals, fine chemicals, even polymers. And it can do all this at room temperature using electricity, often with very little waste. It's like molecular surgery, but with electrons instead of scalpels.
It's amazing. It's like rewriting the rules of chemistry using electricity. But you mentioned something earlier that really caught my attention. Bioelectrochemistry. What exactly is that, and what are some of its potential applications?
Bioelectrochemistry is a fascinating field that looks at the connection between electricity and living systems. Imagine biosensors that can detect diseases in their very early stages by picking up on tiny changes in your body's electrical signals, or implantable devices that use electricity to help nerves regenerate or even control prosthetic limbs.
Wow, that sounds straight out of science fiction. Are we talking about cyborgs here?
Not quite cyborgs, but definitely cutting-edge technology. There's even research being done on biofuel cells, which could generate electricity from renewable biological sources, like the glucose in our blood.
Wait, so we could power our devices using our own bodies? That's mind-blowing. It seems like the possibilities with electrochemistry are truly limitless.
It's a field that spans so many disciplines. It has the potential to revolutionize everything, from medicine and manufacturing to energy and beyond.
I'm totally inspired by all these possibilities. So, as we wrap up our deep dive, any final thoughts for our listeners?
As we've explored, electrochemistry isn't just about abstract equations and reactions. It's about understanding this fundamental language of energy and using it to create a future that is more sustainable and technologically advanced.
Perfectly put. So, to all our listeners, stay curious, keep exploring, and never underestimate the incredible power of those tiny electrons to truly change the world. Thanks for joining us on this deep dive.